Hello and welcome back to 2.4 mechanical vibrations. The network exploded as usual when we are in this classroom, so here we go. 2.4 with revenge. I mean the second part. So far we started with second order differential equations. We did some witchcraft to get it into a nice form. We got the general solution. Then we swapped those C's with A and B. Posed this triangle with all of these cool properties. And then started replacing all of these things in. So now once we are at the point where we have this last row, looking at this, this is the sum of two angles for cosine, right? Cosine of the sum of two angles. So we have C times cosine of alpha minus omega 0 t. But then we are going to swap the order of these two, and then that's going to give us a minus, but the cosine is even function, and then that minus just dies. So we can just write C times cosine of omega 0 t minus alpha. So this one is the actual solution, right, to that's the compact solution, the best possible solution that you can write for the undamped motion, right, the one where it's just going to go forever. And you can see from here, you know that the cosine is the function that goes on forever to infinity, so this one will never stop, right? And over here we have these letters, right? So C is the amplitude. That is how far from the origin, from the equilibrium point, the object is going to go. We have the omega 0, which is the frequency. That's the velocity, right? It's the frequency. They call it circular frequency. It's the angular frequency, right? Angular velocity. So circular frequency. And then we have the phase shift. They call it a phase angle. Off of here, we can find the period t, right? And the period is going to be 2 pi divided by omega 0. If you remember your pre-calc 2 from like 17 years ago, there was that part when you were graphing functions by hand, and we had that the p was 2 pi over b. You remember that formula for sines and cosines? Well, what was it? Was a cosine of bx minus c plus d. That was the major form, right? So you see that b was in front of x. Well, that's your omega 0 now, right? So same formula from just different letters we're using. Same idea. Now you can find the frequency from there, which is, so the frequency ni, that's not a v, that's a ni from, it's a Greek alphabet, which is 1 over period, which is omega 0 divided by 2 pi. Not that big deal. All right, I guess that will, oh, no. There is this, we have to distinguish. So now, guys, one more thing to cover. This is just classification for 3 possible cases when you do the damped motion, right? Which means you are going to introduce the C, and that's C. So now we're going to on the damped motion. We are introducing the C term. So we have good old mx double prime plus cx prime plus kx equal to 0. And we are again going to divide the entire equation by m to get our differential equation like this. Now we're going to put 2p there. Again, same trick like last time for convenience to make our calculations and equations beautiful. So omega is, again, omega 0 is the good old square root of k over m. And in this case, that's the 2p is the c over m, which means that p is just c over 2m. We get to write the characteristic equation for this. So r squared is equal to, r squared plus 2p r plus omega 0 squared is equal to 0. And you know that to solve this equation, you can unleash the quadratic equation. So negative 2p plus minus the square root of 4p squared minus 4 omega 0 squared divided by 2. And you can see why we use the 2p, right? Because it gives us that 4, and I can factor out 4, which comes out in front of the square root, and then that 2 and the 2 on the bottom, they all cancel. So r is equal to negative 2p plus minus 2 times the square root of p squared minus omega squared, omega 0 squared, divided by 2. And from there you see that r is equal to just negative p plus minus square root of p squared minus omega 0 squared divided by 2. So now that you have this, we're going to go and say, all right, so what can happen here? And we know that this part here is called the discriminant, and that's the one that drives whether these particular solutions are going to be real, repeated real, or complex, right? So we have the 3 cases when they are distinct, when they are, right? So we can have, oh, and by the way, from here, P is equal to C over 2m, right? C over 2m, which means that P squared is C squared over 4m squared. So now, when we are talking about only the discriminant, it's going to be C squared over 4m squared minus omega 0 squared equal to 0. And wait, but omega squared was the square root of k over m. So now you have c squared over 4m squared minus k over m. Square kills the root, equal to 0. And we multiply it through by 4m squared. So you get c squared minus 4km equal to 0. There we go. So this one over here is that discriminant, right? Discriminant. And what does the discriminant do? Again, discriminates between 3 possible cases. we can have this discriminant be positive, be equal to 0, or be less than 0. And you are going to have the three cases. So we have the overdamped case. And for the overdamped case, we have that the c squared is larger than for Km, and that will spawn those real solutions, right? With real solutions. And then we have a critically damped case, which is when it's equal. And underdamped case. Where c squared is less than 4km. Now c and k and m are always given in a statement of the problem, so you can always find those and state which of these cases you have. It's the yeah, that's it, right? So the underdamped oscillations, right, are the ones that have that situation where you go like this and it eventually dies out. We're going to see obviously much more of this later. You have a few examples that they worked out in the book. You know all the letters, you can read that. And then they have some of the examples for you to enjoy for homework. I'll see you Tuesday. If I had the mic, I would drop it, but I don't, so there you go.